Good day everyone, especially to you sir. My name is Villamor from BSA2. My topic is extra chromosomal inheritance, cytoplasmic inheritance, cytoplasmic particles, chloroplast, mitochondria. Extra chromosomal inheritance. Some material inheritance indicates cytoplasmic influence which is independent at the nucleus, but this not self-perpetuating and disappears in the subsequent generation. There are other cytoplasmic factors, however, which are capable of perpetuating an independent transmission and may therefore be considered as genetic units fully equal to those in the chromosome. Because of this location outside the chromosome, these genetic factor have been called plasmagens or plasmos or cytogens or plasmids. Extra chromosomal inheritance or inheritance through plasmids tends to be maternal because the zygote cytoplasm is derived from the egg. Therefore, reciprocal crosses give different results. A situation similar to delayed chromosomal inheritance. However, usually phenotypic ratios do not disappear after generation. Plasmid inheritance implies perpetuation through DNA replication. Hence, it is a second system for the transmission of traits. Number 1. Cytoplasmic inheritance. In Chlamydomonas, a single-celled green alga, Sager and her co-workers found in 1960 a number of hereditary variables that failed to show segregation in a chromosomal pattern. For example, streptomycin resistance SR or sensitivity SS appears to be inherited in a regular Mendelian fashion, so the SR times SS products 1/2 SR and 1/2 SS of one resistant strain SR after if SR 500 is empty plus and SS is empty, SS empty, all offspring are SR. However, on the reciprocal cross SS empty times SR empty, all offspring are SS. This effect continues as long as the empty parent is SR. Even after 4 generations of back crossing, SR empty plus SS empty, nor offspring appears. Since such results cannot be explained on the basis of chromosomal segregation, in which a 1 SR, 1 SS ratio is expected, they are ascribed an extra chromosomal factor transmitted only through the plasmating type. Number 2. Cytoplasmic particles. Sunburn in 1943 studied the inheritance of a killer versus sensitive trait in Paramecium aurelia. He found that to be a killer, a paramecium must have the gene segregates in the typical chromosomal fashion and complement of ectoplasmic particulate materials called kappa. Sensitive animals are those that lack kappa. Animals of that genotype Kiki lost their kappa if they initially had it and they are unable to generate it. If kappa is present in cell with a small k gene, kappa does not appear unless some kappa is introduced from another cell. For example, conjugation of killer big kiki and sensitive small kiki strains produces conjugants with very little or no exchange of cytoplasm. Separate killer and sensitive clones are formed depending on the parent from whom they were derived. Introduce autogamy or self-fertilization of the killer, ex-conjugants will produce the homozygotes, big kiki and small kiki. When conjugation is prolonged, thus allowing massive cytoplasmic exchange, both ex-conjugants show the killer trait. Autogamy gives rise to killer and sensitive itself in the big kiki clones but not in the small kiki clones. The cytochrome pigments that kappa utilizes is oxygen, respiration are different from those of the host. Therefore, since paramecium exists quite well without kappa, it presents seems to be an accessory organism or symbiote. Number 3. Chloroplast. In plant cell, chloroplasts are the organelle responsible for photosynthesis. The structure of these organelles, the pigments contained, and and their enzymes systems can all be affected by mutations indicating that chloroplasts are not free from chromosomal genetic apparatus control. But more plastids arise from proplastids, which are able to divide and hereby increase in number. Since plastids arise only pre-existing structures, they are capable of self-replication. The results indicates that there are two kinds of plastids transmitted only through the female. The type of plastids and their distribution are given below. Phenotype of plant: pale, green, variegated. Type of plastid or proplastid: pale, green, pale, and green. From the pale plant would have only the pale plastid type. Those from green only green. Those from variegated either pale or green or mixture of the two types. Neither the genotype of the male gametophyte nor the nuclear genetic constitution of the fertilized egg would be involved in the control of the variations. Number 4. Mitochondria. In Baker's yeast, Saccharomyces cerevisiae and his co-workers were able to identify in 1951 three peptide varieties. A. Segregational nuclear peptides. When crossed with the world-type product ascospores would segregate in the ratio 1, peptide 1 normal. This peptide characteristics is a chromosomally determined trait. B. Neutral peptides. When mated with normal strains, well produced normal or wild-type ascospores and colonies. C. Suppressive peptides. Suppress normal respiratory behavior and process with the normal strains do not most of the diploid cell derived from a zygote are peptide. Most of them, when induced to sporulate in a special environment, give rise to ANSI with 4 peptide spores. The peptide characteristics of yeast have been attributed to deficiencies of cytochrome BC and cytochrome oxidase AA that are normally found in the inner membrane of the mitochondria. The mitochondria also have their own DNA and the cytoplasmic continuity of the neutral and suppressive peptides.